we are discussing about the gate block algorithm. That is, whenever a process puts a request for a data, and firstly, what the kernel has to do is it has to check in the buffer cache that whether the block containing that data is available in the buffer cache or not. So we had seen the algorithm which will be used for gate block. So what the kernel does is if it finds that the block containing the data is available in the buffer cache, then we can have two different situations, that the buffer is locked by some other process. So if the buffer is locked by some other process, then the process which has put the request, that has to go to sleep mode until and unless the buffer is free. So when the buffer becomes free, the process will wake up and it can get the corresponding buffer. And in case the buffer is not locked, that is, data is available in the buffer and the buffer is free, then the kernel has to mark the buffer as busy, or it has to lock the buffer. Then the buffer has to be removed from the free list, and the buffer is to be returned to the requesting process. The other situation that we can have is that the buffer is not in the hash queue, or the data block is not in any of the buffer cache. In that case, we can have two different situations. So if the data is not available in the buffer cache, we have to get the data block from the disk, put into one of the buffer cache. Okay. So for that, what is needed is we have to get a buffer which is free. So accordingly, I can have two different situations, that there is no buffer on the free list. That is, the free list is currently empty. So again, then the process has to go to sleep mode until and unless any of the buffer becomes free. So in our earlier case, it was a particular buffer which was to be free, and until then the process has to remain in the sleep mode. And in that case, whenever any of the buffer becomes free, then a buffer will be used from that free list following the least recently used approach, and that will be given to the process who has requested for it. And if there is a free buffer, a buffer on the free list, then a buffer will be taken from the head of the free list. So that particular buffer will be removed from the free list. Then we have to check that whether the buffer has been marked as delayed write or not. So if the buffer is marked as delayed write, then obviously this buffer cannot be overwritten by a new block of data until and unless the content of the buffer is saved onto disk. Okay, so if the buffer is marked as delayed write, then asynchronous write buffer to disk is initiated. So we said that it is asynchronous in the sense that kernel just initiates the disk write operation, but it does not wait for the disk write operation to be complete. Rather, what it does is, after initiating this disk write operation, it tries to find out whether there is some other buffer which is free or not, which can be given to the process immediately for loading the new data block. Okay. But in case the buffer is not marked as delayed write, in that case the buffer will be removed from the old hash queue because it was containing some data, so it was present in one of the hash queues, and the buffer has to be put into the new hash queue, where this new hash queue will depend upon which block of data is being read and put into the buffer, and the buffer will be returned to the process. Okay, now this buffer can be used for reading in the new block and putting into the buffer. So following this algorithm, you find that we had drawn one diagram which says that we have 4 different hash queues, and in every hash queue we have, say, 3 buffers containing some data block. Okay, and out of these 9 buffers, we have a number of buffers which are on the free list. Now in this situation, if a process puts a request for, say, buffer number 98, block number 98, okay, so immediately 98 mod 4, this mod function will be computed. After computation of this mod function, you find that block number 98 should belong to hash queue 2. So the kernel just checks hash queue 2, and here it finds that block number 98 is present in the hash queue. Okay, but this is not present in the free list. Okay, that means though the data block is present in the buffer, but this buffer is currently being used by some other process, or the buffer is locked. So the process has to go to sleep mode, and that can wake up and get this buffer only when the buffer is released by the process who is already using it. Okay, but if a process puts a request for, say, block number 3, then block number 3, which is present in the hash queue 3, and it is also present on the free list. Okay. So the process can immediately get this block number 3 and it can use this buffer. Now suppose a process puts a request for, let us say, any buffer, any block which is not present in this diagram, say block number 7. So whenever a process puts a request for block number 7, immediately you compute 7 mod 4, which will give you a value 3. That means block number 7, if it is present in the buffer, should reside in hash q3. So kernel has to check this hash q3. Here it finds that block number 7 is not present. That means now the kernel has to make one buffer, free buffer available to the process where this block number 7 can be brought in. So kernel checks this free list, comes to the head of the free list. Now it is block number 3, the buffer containing block number 3. It takes out this particular buffer from the free list. Okay. Now if this buffer is marked as delayed write, in that case what the kernel will do? Kernel will simply start writing this block number 3 from the buffer into hard disk. Okay. So right now this buffer will not be present in the free list because it has already come out of the free list. Okay. The kernel just initiates the writing operation, and after that it does not wait for this write to be over. It checks for the next buffer in the free list. The next buffer in the free list is buffer containing block number 5. Now if this buffer is not marked as delayed write, then the buffer will be given to the process for getting in this block number 7. Okay. Now here you find that the earlier hash queue in which this buffer was present is hash queue number 1. But when this block number 7 will be placed into the buffer will not remain in hash queue 1, but it has to reside in hash queue 3. And because this is recently used, so where you put this buffer, it will come at the tail of hash queue 3. So it will come here and it will contain the block number 7. Okay. And this particular free list will now be something like this. Okay. So until and unless this block number 3, writing this block number 3 into disk is complete, then header of the free list header will be block number buffer containing block number 4, and others will remain undisturbed. Okay. So this is how the block read operation has to continue.
When the process goes into sleep mode, then why to continue with this program? Because we have written continue under the sleep statement.
Yeah, the process goes to sleep mode, not the kernel. Kernel has not. See, this algorithm is for the kernel. This algorithm is for the kernel, and it is not necessary. Maybe some other process has put. No, not necessary. It may be for some other process. This process has gone to sleep mode. Okay, but kernel continues in this while.
But the block number for which it is searching is not there.
That is what I am saying. Maybe some other process has put a request for another block. So why should the kernel wait until and unless the block for this process has been allotted? The kernel can consider the block request for some other process. Okay. The process will not wake up until and unless this buffer becomes free. But the kernel is not going to sleep. So this algorithm is meant for the kernel, it is not for the process. Clear? Okay. So as we have seen the get block algorithm, in the same manner, let us see that what will be the structure of the algorithm or nature of the algorithm when a buffer is made free by a process. Okay. So accordingly, we have an algorithm which is called block release, or say B release. So when a block is released, before that the situation that we can have is maybe some process has gone to sleep mode for this particular buffer to become free, or we can also have a situation that some other process might have gone to sleep mode waiting for any buffer to become free. Okay. Now whenever a buffer is made free by some process, in that case the requirement of both kinds of processes are met. A process which is waiting for this particular buffer to become free, or a process which is waiting for any of the buffers to become free. Okay. So once a buffer is released, what we have to do is we have to wake up both the kinds of processes. So first, what we have to do is, let us write wake up all processes the processes which are waiting for any buffer to become free. Okay. We also have to wake up the processes which are waiting for this particular buffer to become free. So we write wake up all processes waiting for this buffer okay. Now once they are waken up, then I have a situation that I have to return the buffer to the free list. Now why do I return it? We have said that whenever a buffer is released, that means previously the buffer was being used by some process, so it becomes the most recently used buffer. So normally we will put this buffer at the tail of the free list, so that this is the buffer which will be last among all the buffers in the free list to be overwritten. But we can have two different situations when this buffer can go to the head of the free list. One such situation we have said that if the buffer contains an invalid data, because it is invalid, the data contained in the buffer is invalid, so no point maintaining that data for a longer period. We would like to override that buffer with a valid data as early as possible. So if it is found that the buffer contains an invalid data, then instead of putting the buffer to the tail of the free list, you just put it at the head of the free list. There is another situation when the buffer can go to the head of the free list. That is when the buffer data becomes old. Okay. So I can have, I'll come to what do we mean by buffer data becoming old. So we can check the condition that if buffer contains valid and not old, okay, then NQ buffer at end of free list. Okay. Else, that means the buffer content not valid or the data contained in the buffer is old. In that case, we have to NQ buffer at the head of the free list. Or beginning of free list. Okay. And following that, what you have to do is we have to set the status field in the buffer. Earlier, the status field was indicating the buffer was locked. Now we have to unlock the buffer and return from there. Okay. So this is the algorithm which will be used for block release operation. Now coming to this data buffer content not old, you have seen that when a buffer is marked as delayed write, and that is the buffer which is to be overwritten, selected to be overwritten by a new block, we cannot overwrite the content of that buffer because the buffer was marked delayed write. The moment I find that the buffer is marked delayed write, the kernel simply initiates writing the content of the buffer onto the disk. But when the disk writing is complete, then the buffer has to be returned to the free list. When do you return? Where do you return it? Because the content of the buffer is already saved onto the hard disk. That means the hard disk copy of that block is also updated. That means the content of the buffer becomes old. And in any case, here the buffer is accessed not by a process to process, not by any of the process to process the data contained in the buffer. But the buffer is accessed by the kernel only to save the updated data onto the disk. Okay, so in true sense, the buffer is not most recently used. But the buffer is still least recently used because it was selected by the kernel to be overwritten. But because the kernel found that it is marked as delayed write, the data was not able to overwrite the content of that buffer immediately. Okay, so even in such situation, after writing the data of the buffer onto the disk, the buffer will be marked as old. Then while releasing the buffer, the moment it finds that the buffer is marked as old, okay, the buffer will be enqueued at the header of the free list, so that the next time the same buffer can be used for overwriting the content with another block data. Okay, so these are the two situations: either the contents of the buffer not valid, or the content of the buffer is old. In that case, buffer will be enqueued at the head of the free list. Otherwise, the buffer will be enqueued at the tail of the free list, in which case this will be most recently used. Okay. Now, whenever a process wants to read the content of a particular data block, then the procedure which is invoked is what is called block read operation. And it is the block read operation which makes use of the get block algorithm. Okay. So, in case of block read operation, the input to this algorithm will be the file system block number and output will be a buffer containing valid data. Okay, the data which has been requested. So, in this block read operation, the first operation which has to be done is you get a buffer for the block. The block which has been requested. Okay, and it is here that the get block algorithm is invoked. Right. So, whenever the kernel tries to get a buffer for the requested block, it invokes this get block algorithm, it executes this get block algorithm. Then output of the get block algorithm can be either a free buffer or a buffer containing the block that is requested, as we have seen in get block algorithm. So, if a buffer containing the data block is found, in that case that data block, that buffer will be returned to the process. Otherwise, a free buffer will be returned to the process. Okay. So, here if we find if buffer data is valid, valid includes that the data containing this particular block number which is requested. In that case, you simply return the buffer to the process. Okay. Now, if there is no buffer containing this block that is requested, then obviously I cannot return the buffer containing the data. I have to return a free buffer. Okay. So, that free buffer will also be returned by this get block algorithm. Right. So, once the process gets this free buffer, then the process has to initiate the disk read operation, because disk read operation is not taken care of by this get block. Okay. Then what you have to do is you have to initiate disk read, okay, obviously into the buffer. Okay. And since the process has requested for this block and the block has to be read from the disk, so it initiates the disk read. And naturally, until and unless this read is complete, the process cannot continue. The process cannot perform any other task. So the process has to go to sleep mode. So this sleep is again for the process. The process has to go to sleep mode on event that disk read is complete. Okay. And once disk read is complete, then the buffer containing the new block can be written. Okay. So this will be the block read operation whenever a process wants to get data from a particular disk block. Now, the performance of the system can be further improved if we incorporate some facility of reading blocks ahead of time. Okay. That is based on the assumption that whenever a block is requested by one process, then it is quite likely that the next block containing the same data file, part of the same data file, will also be requested next. Okay. So whenever you start reading a particular block, then what we can do is we can start reading the next block containing the data of the same file asynchronously. The first data block, the first block read has to be synchronous. The second one may be asynchronous, because the process has to wait until and unless the first data is read into the buffer, but it need not wait for the second block. Okay. So second block, when the process needs the second block, hopefully the second block will be available because of that asynchronous read operation that is already initiated. So accordingly, we have an algorithm which is called block read ahead algorithm. So that is, let us put it as block read ahead. Okay. So in this block read ahead, what you have to do is you have to check that whether the first block is available in the cache or not. Okay. So if the first block is not in the cache, okay, then what we have to do is we have to get a buffer for the first block. So naturally, this is the get block operation that has to be done. Okay. So after getting a buffer for this first block, then you have to initiate disk read. So in this case, the block that will be read is the first block. Okay. After that, you check whether the second block is available in the buffer or not. So if second block not in cache, okay, then we have to get a buffer for the second block also. So again, get block algorithm has to be invoked, and following that we have to initiate disk read for the second block. Okay, and in this case, this read has to be asynchronous. It has to be asynchronous because the process immediately needs the first block. It does not immediately need the second block. So the process has to wait until and unless the first block is dead. But once the first block of data is available, the process can continue, and reading this read for the second block can continue in the background. Okay. So it simply initiates reading of the second block, and this read operation is asynchronous. Okay. And after that, here we have initiated reading the first block. Okay. here we check if first block in cache okay, then what we do is you return buffer. Okay, so here what we'll do is the process will wait until and unless the first block is read into the buffer cache. When the first block is already read, in that case the buffer will be returned to the calling process. So this is a block read operation which can be used to improve the system performance. Okay, and of course here I didn't expand it. Here another statement that you can put is sleep until the first block is already read, and you can return only when the first block, the reading of the first block is already complete. Okay, so as we have done all these read operations, similarly we also have to see that what will be the operations for writing a block onto the disk. Okay, so accordingly we can have algorithms for block write operations. In case of block write, what you have to do is you simply initiate disk write okay, then you check whether this write operation is synchronous or asynchronous. Okay, so if this IO operation, that is the write operation, is synchronous, then obviously the process has to go to sleep mode until and unless the writing operation is complete. Okay, then you sleep event IO is complete. Okay, and after that, once the writing is complete and the process wakes up, then the buffer has to be released. So release buffer, and for this release buffer operation, the algorithm that has to be invoked is the block release algorithm, and it is the block release algorithm which will take care of whether to put this buffer at the head of the free list or at the tail of the free list. Okay. Now, if this IO operation is not synchronous, so else whether it was a delayed, whether this write operation has been initiated because of a buffer being marked as delayed write. Okay. So in that case, what you do is you check whether the buffer was marked as delayed write. So in case the buffer was marked as delayed write, then what we have to say is after the writing is complete, then what we have to do is to mark the buffer as old and return the buffer at the head of the free list. Okay. So in this case, you mark the buffer old and return buffer at head of the free list. After the writing is complete. Okay. So this is how a data block from the buffer will be written onto the disk, and following that the buffer will be released and it will be put into either the head of the free list or at the tail of the free list. Okay. Now, so far all our discussions was in the logical level, that is, we have assumed that whenever a process puts a request for a buffer for a particular block, you have to read the block from the disk, put it into one of the buffers. Okay. But for that, what is needed is that you have to know that what is the address of the block on the disk. And not only here, even in case of demand paget memory management system, we have said that in case of any page fault, the operating system has to find out the disk address of the page which is requested, which has led to a page fault. And this disk address, we have said, is available from what is called a file map table. Okay. Now, when you come to, now I'll take examples from Unix operating system. In case of Unix, the information of file map table is stored in a data structure which is called an inode or an index node. Okay. So that is called an inode or index node. This index node stores the disk layout of every file or every directory in the file system. Okay, so for every file in the file system, we have an index node. Similarly, for every directory in the file system, we will also have an index node. These index nodes are data structures which are also stored on the same file system or on the same disk. So if you look at the disk layout is something like this. As we said, the disk consists of a number of blocks. Okay. So different blocks on the disk will contain different information. So let me put this as a linear map. We'll have initial block, which is called a boot block. Okay, this boot block usually contains the boot volume, that is a part of the operating system, which is loaded in the main memory when the system is booted. Then next, we have another block, one or more blocks, which are called super blocks. Okay, the super block contains information about the state of the file system. Followed by that, we have a number of blocks which actually contain the inode list. And after this inode list, we have the actual data blocks. Okay. So this is the logical layout of every file system or every disk. We have initially an initial block which is called a boot block that contains the boot volume. Following that, we have one or more blocks which are called super block. This super block contains the state of the file system. Following that, we have a number of blocks, maybe one or more blocks depending upon how big is the file system. So as I said, that on the file system, for every file as well as for every directory, we will have an inode. Okay. So depending upon how many inodes we have in that file system, actually this number of inodes is decided by the administrator while installing the operating system. Okay. So depending upon how many inodes you have on the file system, that decides that what is the size of the file system, how many files or how many directories you can have on the file system. Then following those blocks, the actual data blocks start. So whenever the content of any file or the content of any directory is to be stored, those are actually stored in these locations, and the location informations are in the inode list. Okay. Again, some of the inodes are put into the super block. We'll come to those things in details later. And along with that, the super block contains many other information. So the informations which are contained in the super block are, one of the information is how large the file system is. This information is contained in the super block. Similarly, how many files the super block, the file system can store. Okay. It also contains an information about where to find the free space on the disk. Okay. So where to free space or free blocks on the disk. It also contains the information about what are the free inodes. Because as I said that for every file or for every directory, we have to have a particular inode. So whenever we want to create a new file or we want to create a new directory, then out of the inodes which are free in the inode list, one of the inode has to be allocated to the file or to the directory. Okay. So the superblock also contains information about that what are the free inodes on the inode list. Okay. So you find that in many cases, I don't know whether you have faced any such situation or not. When we try to open a new file, create a new file, or we try to create a new directory, you get an error message that file system full, even though there is lot of disk space available on the file system. But even then, I can get an information of file system full. That is only because maybe the number of inodes which are assigned to that particular file system, the number of inodes have been exhausted. I don't have any free inode, though I have free disk space available. So even in such case, we will get an information of disk file system full. Okay. So these are the contents of the super block. Similarly, coming to the inode list or a particular inode, as we said that every inode contains the disk layout of any file or the disk layout of any directory. So we can have, or usually we have two types of inodes. One is called disk inode, other one is called in-core inode. Okay. So as I said that the inodes are stored on the disk in this inode list. Whenever you open a file, because as I said, even the disk layout of the file is contained in the inode. So whenever I open a file and I want to read successive data from the file, okay, that means to find out that where that data resides or where the block of the file or page of the file resides on the disk, I have to refer to this inode. So for every disk access, I have to refer to inode, which usually needs that one additional disk access for getting the information from the inode. So the number of disk accesses will increase. So to reduce that, what is done is whenever you open a file, the inode corresponding to that file is copied from the disk to main memory. Okay. So as long as the inode exists in the main memory, and it is usually maintained in the systems area or operating systems area. So as long as the inode exists in the main memory, it is called an in-core copy of the inode. Okay. So an inode on the disk will be called a disk inode. An inode, a copy of that in the main memory will be called an in-core inode. These inodes have a particular structure so that it can contain different informations. So first let us see that what is the structure of the disk inode, because whenever the inode is put into the main memory, it will contain some additional fields additional to those fields which are there in the disk inode. Okay. So let us see that what is the disk inode structure. Thus, disk inode contains a number of fields, and every field will contain some information. The first information that you have to have in the disk inode, or the first field that you have to have in the disk inode, is the ownership specification of the file. That is, you have to specify that who is the owner of a particular file, and that specification is contained in one field in the disk inode. Okay. Then in case of a Unix operating system in particular, we have two types of ownership. One is individual ownership, other one is group ownership. Because you might be knowing that whenever an account is created, an user is attached to a particular group. So we have individual ownership. Along with that, we also have group ownership. So the first ownership field that is contained is the individual ownership. That is, who is the owner of the file. And second ownership that we have is group ownership. So we have two fields in the disk copy of the inode. One indicate the individual ownership, the other one will indicate the group ownership. Okay. Then the third field that you have in the disk inode is what is the type, because as we said that every file will have an inode, similarly every directory will also have an inode. So I have to specify that what is the type of this particular information, whether this inode is the inode of a file or this inode is the inode of a directory. Okay. So in the type field we have to specify whether it is a regular file or it is a directory. Okay. Then we have what is called permission field. And this permission field is usually specified in the form of read, write, and execute. So whenever you give directory listing, you might have seen that you get RWX kind of information, and there are three sets of RWX. So I get RWX, RWX, and RWX. First three RWX is meant for the owner of the file, that is this owner. R means read permission, write, W means write permission, X means execute permission. So when all these R, W, and X they are present, that means the owner of the file has got all the three permissions. He can read the file, he can write into the file, the owner can also execute the file. The next RWX is meant for the group. That means every member belonging to the same group will have the permissions which are given in this RWX. Okay. In some cases, you will find that I have only R, after that I have an underscore, then an X. It indicates that the other members of the group will have read permission, they will have execute permission, but they don't have write permission. They cannot modify the file. The third set of RWX indicates the access permission, the permission given to other users of the system who is neither an owner and nor belong to the group. Okay. Then among other fields, you have the fields corresponding to access time, that is when the file was last accessed. We have also the modification time, that is last when the file was modified. We also have the time when the inode was modified. This is the time information when the inode was last modified. So these informations also you have on the inode. Obviously, you have to have information about what is the size of the file. That means how many bytes the file occupies. And the most important info, of course, all of them are important, but so far as the data access on the disk is concerned, we have to have the information about the disk addresses of different data blocks. Okay. So these are the block addresses of different data blocks of that file, and this is also called the inode table of content, or TOC. Okay. So all these informations of a particular file or of a particular directory will be contained in the inode, and these are the fields of a disk copy of the inode. And as I said that whenever you open a file, then the disk copy of the corresponding inode will be read from the disk, and it will be put into the main memory when it will be called an in-core item. Okay, so we'll see the details of that in the next class.